Alright, so here we're going to talk about some implications of derivatives and differentiability. So if we are told that the derivative of function f exists at point A, right? That actually has a lot of implications about the continuity of a function at point A. In general, differentiability implies continuity. What does this mean? Well, if we are told that we have a derivative that exists of a general function f, right, at a point such as a, we can also assume that that function is continuous at point A, right? This is a theorem. And I'll just give a quick proof to that theorem. So essentially, if we are told that the function is continuous at point A, right, we can write this as limit as x tends to a of f of x is equal to f of a, right? This sort of comes from our previous discussions about continuity. If we were to manipulate this a bit, we can write this as limit as x tends to a f of x minus f of a, right? Let me just write proof. Okay. And we need to show that this equals 0 in order to show that differentiability. Well, in order to show differentiability implies continuity, we have to somehow show that a function being differentiable implies that this expression here is also true. Well, one thing we could do is we can multiply by x minus a, right? And because I'm multiplying the numerator and denominator, it's like multiplying by 1. Some of you might be wondering, wouldn't this be multiplying by 0 on both sides? But because we have this limit thing, we're not really, like, although if we were to evaluate it, like, it would become 0. Like, if we were to plug in a for x, it would become 0. Because we're doing this under limits, it's not really 0 yet. So it's completely valid, right? And then now what we can do is we can write this as limit as x tends to a x minus a times limit as x tends to a f of x minus f of a divided by x minus a. We know that this right hand side over here is just the definition of the derivative at point A, so we can write that as f prime of a, and then this right here is just 0, and then that evaluates to 0. So we went from this limit as x tends to a of f of x minus a, and we showed that it's 0. So essentially, if we know a function is differentiable at point A, right, we made that assumption when simplifying this expression into this. Otherwise, we couldn't have done that. If we know a function is differentiable at point A, then we know it's also continuous at that point. So that's one of our big implications of knowing whether a function is differentiable at a point and whether the derivative exists at a point. Now let's move on to our second implication. Or this is more like a property. So property 2. Okay. So remember the intermediate value theorem. So first let's just recall the IVT, the intermediate value theorem, stated that if we know a function is continuous, like given given f is continuous in the interval a to b, right? Then every value between f of a and f of b must exist in that interval for some x, f of x, right? So every like value between this interval must exist in f of x for some value x, right? So that was the intermediate value theorem for just like a function f, right? Now there's also an intermediate value theorem of derivatives. So theorem 2. IVT for derivatives. Basically, if a and b are 2 points in an interval where f is differentiable, right? Then f prime takes on every value between f prime of a and f prime of b. So I'm not going to give you the proof of this because I think it's a bit out of scope for just a beginning calculus class, but if we know the derivative of f prime of a, and if we know the derivative of f at point a, and then we know f prime of b, and we know that a and b, right, in that interval, like f is differentiable, which we know because differentiability implies continuity, it's also continuous in that interval, we can know that f prime will take on every value between f prime of a and f prime of b. And so it's very analogous to the other intermediate value theorem of just like regular functions. So that's one good thing to remember.